Hello, so today we are going to go over Newton's second law of motion. So this is Physical Science Unit 4, Lesson 11. So acceleration is an unbalanced force that causes something to accelerate. So acceleration is directly related to the size of the force and the direction of the force. So we always have to look at how much force is being used, and then of course what direction that force is being applied in. So it accelerates in the direction that you push or pull. So here we have the cart that's full of newspapers. So the force that he's put on it is going to move forward with him. So checkpoint. According to Newton's second law of motion, an object will accelerate if you apply one kind of force to it. Just think about the previous slide. And then, yep, it's an unbalanced force, because if it's balanced, it's not going to move. So we have to have that unbalanced force to move it into a direction. So in other words, if we have a large force, so notice the capital F here, and we were pushing an object, we are going to get a large acceleration. But now if we take the same object and we have a small force, it's going to have a small acceleration. So if we push it twice as hard, to accelerate twice as much. So in order to get it to go as far as the large force, we have to push it twice as much. But there is a twist in this situation. So acceleration is inversely related to the mass of the object. So if you see here, we have the same force that's being used. The only thing that's different is the mass of the object. So here we have a Hummer. Down here we have like a small smart car. So if you use the same force to move it, the small car is going to accelerate faster and longer than the Hummer here will. So you can see that if you're driving down the road, if you're in a car versus a semi-truck, if you're both trying to get up to 55 miles per hour, the car is going to get there sooner than the truck. So Newton, that brilliant genius that he was, observed these rules of acceleration and came up with his second law of motion. So it's both a formula and a law. So acceleration of an object is directly proportional to the net force and inversely proportional to its mass. So that's where we get our formula F equals ma, which is the force is equal to the mass times acceleration. So another checkpoint here. According to Newton's second law of motion, if we have a rigid, unchanging mass and we observe it accelerating, what must be happening? Okay, so here we have that's an unchanging mass, so mass is not changing, but we do see that it is accelerating. So what's happening? So think of the formula, F equals ma. If mass doesn't change and acceleration is increasing, so the other part of that equation is force, so what's happening to that force? Well, if acceleration is increasing, that force also must be increasing. So force must be being applied to the mass. So quick question. A force of 30 newtons is exerted on an object, resulting in the acceleration of 5 meters per second squared for the object. What will be the object's acceleration if the force doubles? Alright, so let's work through this together. So we have our formula, F equals ma. We're just going to punch in the numbers first. So you can punch in the force, which is 30 newtons. We put that in here. We don't know the mass, but we are told the acceleration. So you can put the acceleration in for here. We're going to solve for mass. So it's just simple algebra here. So moving this 5 over to this other side, so you have to divide by 5 meters per second squared, and you're going to end up with 6 kilograms. So now what the question is what will the object acceleration be if the force doubles? So now we can double this, so we have 30, double it, you get 60. The mass is not going to change, so the mass is still going to be 6, but now for force you're going to have 60, and for mass you're going to have 6. So then we can work through that equation, and we find that your acceleration, which then is equal to force divided by mass, and you're going to get 60 divided by 6, so that's going to give you 10 meters per second squared. So if you notice, if your force doubles, so does your acceleration. So another checkpoint here. So what force is needed to give a 0.5 kilogram arrow an acceleration of 196 meters per second squared? So we start with our equation, F equals ma. Now we just punch in for mass. We're given that it's 0.5 kilograms, so we punch that in for m. We're given that acceleration is 196 meters per second squared. Punch that in, do the multiplication, and you get that force is 98 newtons. Okay, because remember, newtons is kilograms times meters per second squared. We just replace all that with that in. So we have calculating acceleration. So here, in all the other examples so far, we were given what acceleration is. We were given the number, or we were asked to find the number. But what if we're given more detail, but we're not given exactly what acceleration is? Well, here is how we can find acceleration. So if you notice here, we have the final speed in meters per second minus the initial speed in meters per second, all divided by time in seconds. So if you notice, on top we have meters per second, and below we have just seconds. So if we have meters per second for our units, we can combine all that together and just make it meter per second squared. So it's a little easier to write at that point. So we can shorthand all of this to the acceleration is equal to your speed of your final minus your speed of your initial all over time. But wait, we don't know what speed is or how to calculate it. So how can you calculate acceleration? Well, a lot of times they're either going to give you what speed is, and then we'll show you here in a second how we can calculate that as well. So first you need to know the units of force, mass, and acceleration. So this should be a review for you guys. So force is always in newtons. The units for mass are always in kilograms. And acceleration is always meter per second squared. Because remember, a newton is kilograms times meters per second squared. Alright, so what is speed? So we have average speed and then you have regular speed. So basically speed is just a comparison of time and distance. So we're just looking at how far you traveled in a certain amount of time. So acceleration. So we have acceleration. So I change in velocity, so that you're either going to be speeding up, which is a positive acceleration, slowing down, which is going to be shown as a negative acceleration or deceleration, or just that change in direction. Alright, so let's actually work on calculating some speed. So if you notice, I have a pyramid here, and I have it divided into thirds. So if I can put an S here for speed, we're going to put a D on top for distance, and we're going to add a T here for time. So you can think of this as distance divided by time is going to give you speed. Okay, so you can kind of look at it this way. So we're wanting to find speed, so therefore must be distance over time as our equation. So here you're going to have speed is equal to distance divided by time. Alright, so Riley chucks a water balloon at a big, mean-looking guy at the park. Running for his life, he travels 100 meters in 9.83 seconds. So what is his average speed? So we want to find S. We have to take the distance divided by time. So the distance we are told is at 100 meters. The time is at 9.83 seconds. So we do the division here, and we know that his speed was 10.17 meters per second. So now we are given speed and time, but we want to find the distance. So now you can look at, here's our line. So we're trying to solve for d. Therefore, it must be time times speed. So now we'll look at that multiplication. So if you ran 50 kilometers per hour for 20 minutes, how much distance would you cover? So you have distance equals speed times time. So we just manipulated that first equation to now solve for distance. So now we just have to plug in our times, but if you look, here we're in minutes, here we're in hours, so we do have to add in that calculation to convert it. So at the end here you get that he covered 5 kilometers. Alright, so now if we're given distance and speed, we have to calculate time. So this is what we're trying to find. So draw the line. You have distance over speed. So you can think of that as being divided again. So that's why you get the time is equal to distance over speed. So it's an original equation that we manipulate so that we can punch in the numbers that we know and solve for the unknown. So Marcy doesn't want to be late for class, so she rushes to McDonald's at lunch. How much time would it take Marcy to walk 2 kilometers to McDonald's for a Big Mac if she walks at the rate of 4.5 kilometers per hour? So here we don't know the time, but we know the distance, and we know the speed. So now we can just punch those into the equation. And we come up with that she is 0.44 hours or 26.4 minutes. Alright, so now we can find the acceleration using this equation because now we understand what speed is. So let's practice. So Rob is really bored one Saturday night and goes outside to study the nocturnal habits of mice in the hayfield. He sees a mouse scurrying along at 0.1 meters per second, but it hears him and starts to scurry for safety. In just 3.7 seconds, it accelerates to 0.9 meters per second. So we're going to find the acceleration. So if we have our equation here for acceleration, his final speed is this 9 or 0.9 meters per second. That's SF. So his final speed. His initial speed is this 0.1 meters per second. So that's SI. and time is going to be just 3.7 seconds. So now we just have to punch those into the equation and solve. So we punch in the final speed minus the initial speed, so that gives us 0.8 meters per second. We are going to divide that by time, which is at 3.7 seconds. And so that's going to give us an acceleration of 0.216 meters per second squared. So a roach moves down the hall at 1.2 meters per second. When he sees a janitor coming down the hall, he begins to run. After 3.2 seconds, he is moving at 3.6 meters per second. What is his acceleration? So we know our acceleration formula. So his final speed is just 3.6. His initial speed is at 1.2. And the time it took him to change is 3.2. So now we can just plug those in. So 3.6 minus 1.2, that's all going to be divided by 3.2. So you get that the roach accelerated at 0.75 meters per second squared. So this is just knowing what equation to use, so one is asking you to find, and then be able to punch the numbers given into that equation and then just multiplying and dividing it out to get your answer. So let's practice this one. So while waiting for his mom to come out of the hairdresser's, Sean accidentally puts the car in gear and it begins to roll forward. How far would the vehicle travel if it moved at 34 meters per second for 2.5 seconds? So at first you might be thinking that they didn't give you enough information here, because we know that the final speed is just 34, but you might be thinking that we don't have an initial. But if you read, he puts the car in gear, so he's starting from 0. So the initial here is going to be 0 meters per second, and then time is at 2.5. So you have 34 meters per second minus 0 meters per second, all divided by 2.5 seconds. So you get that he accelerated at 13.6 meters per second squared. Alright, so what is the mass of a car if a force of 2,500 newtons gives the car an acceleration of 200 meters per second squared? So that goes back to the first equation that we were talking about, of force equals ma. So force equals mass times acceleration. So we just punch in the numbers given for force, punch in the number for acceleration, solve for m, and you get that the mass is 12.5 kilograms. If you have any problems calculating this out, please let me know, and we can work on helping you pull out the information from the question and put it in the correct equation. So this is a big one down here. So remember that your newtons is equal to kilograms times meters per second squared. So anytime you end up with your units being kilograms times meters per second squared, you can replace all of that with in. Okay, if you have any questions, please make sure that you're staying after class for office hours and asking, or sending me a email. Thank you so much.